This research paper, titled Cost of Pass, an economic framework for evaluating language models, is authored by Mehmet Hamza Erol, Batu El, Mirak Suzgun, Mert Yüksekgönül, and James Zhou from Stanford University. It addresses a critical challenge in the adoption of AI, specifically language models, by examining how their economic value stacks up against the costs of using them. At its core, the paper proposes a new way to evaluate language models by integrating both their performance accuracy and the inference costs involved. Inference costs refer to the computational and monetary expenses of running these models to generate outputs. The authors argue that simply measuring accuracy isn't enough. We need to consider the trade-off between getting the right answer and how much it costs to get there. They introduce a key metric called cost of pass, which is defined as the expected monetary cost of generating a correct solution. In simple terms, it's about calculating how much money you have to spend, on average, to get a reliable and accurate response from a language model. To make this more comprehensive, they define the frontier cost of pass as the lowest possible cost of pass you can achieve using the best available models, or even comparing it to the cost of hiring a human expert. This frontier acts like a benchmark, showing the most efficient option in the current landscape. The paper draws from economic production theory, specifically concepts from economists like Farrell in 1957 and Eigner and colleagues in 1977. These ideas help model how inputs, like computational resources, lead to outputs, such as accurate AI responses, while accounting for inefficiencies or errors. In this context, it's adapted to handle the stochastic nature of language models, where outputs aren't always perfect due to various uncontrollable factors. Through their analysis, the authors reveal several important economic insights. First, different types of language models excel in different tasks based on cost effectiveness. For basic quantitative tasks, like simple math problems, lightweight models are the most efficient because they require less computational power and thus lower costs per correct output. On the other hand, large models, which have vast amounts of parameters and knowledge, are better suited for knowledge-intensive tasks, such as answering factual questions or summarizing information. Meanwhile, reasoning models, which are designed for deeper problem-solving, prove most cost-effective for complex quantitative problems, even though they have higher per-token costs. The second major insight is about progress over time. By tracking the frontier cost of pass over the past year, the authors show significant advancements in the field. For complex quantitative tasks, the cost has been roughly halving every few months, indicating rapid improvements in AI efficiency. This progress highlights how the AI ecosystem is evolving, making these models more viable for real-world applications. To understand what's driving this progress, the paper examines what they call counterfactual frontiers. This involves estimating what the cost efficiency would look like if certain model classes didn't exist. For instance, they find that innovations in lightweight models have been essential for pushing the frontier in basic quantitative tasks. Large models have been key for knowledge-intensive tasks, and reasoning models have driven advancements in complex quantitative areas. This analysis underscores that specific types of model innovations are tailored to different challenges, contributing uniquely to overall efficiency. Finally, the authors investigate common inference time techniques, such as majority voting, where multiple model runs are averaged for a consensus, and self-refinement, where the model iteratively improves its own output. They assess whether these methods reduce costs effectively. Their findings indicate that while these techniques can boost accuracy marginally, the additional costs they incur often don't justify the benefits. In other words, the extra computation required doesn't provide enough value to make them worthwhile in most cases. Overall, the paper emphasizes that the primary drivers of cost efficiency in language models are advancements at the model level, rather than tweaks during inference. This economic framework provides a principled tool for researchers and practitioners to measure progress, compare models, and guide decisions on deployment, ensuring that AI adoption is based on true economic viability.